The Sun will become a white dwarf. A white dwarf will eventually become a black dwarf. So what will a black dwarf become? We know that about 5 billion years from now, the Sun will expand into a red giant, so large that it could even engulf the orbit of Mars. After that, as its outer layers are shed, all that will remain is a small core, a white dwarf. When a white dwarf first forms, its surface temperature can reach hundreds of thousands of degrees, and its internal temperature can exceed 100 million degrees. Ignoring dark matter and proton decay, a white dwarf has no internal energy source. The only way it can radiate energy outward is through its remaining residual heat. As a result, it will enter a period of rapid cooling. In just a few billion years, the surface temperature of a white dwarf will drop from hundreds of thousands of degrees to only a few thousand degrees. After that, the cooling rate will gradually slow down, eventually approaching the temperature of the cosmic background. That is, close to absolute zero. This process takes an amount of time, far longer than the current age of the universe. That is why, to this day, we have never observed a fully cooled white dwarf. Apart from the fact that time itself has not allowed it, a white dwarf at this stage would already be completely cold, and would emit almost no radiation at all. It would appear as a pitch-black sphere. It might look somewhat like a black hole, just with much smaller mass, and far weaker gravitational effects. At that point, calling it a white dwarf no longer seems appropriate. So scientists gave it a more fitting name, a black dwarf. So is a black dwarf the Sun's ultimate fate? In fact, a black dwarf is a special type of white dwarf. At its core, it is still a white dwarf, just one with an extremely low temperature. That means the internal matter of a black dwarf, like that of a white dwarf, exists in a state of electron degeneracy. So what is electron degeneracy? It means that under extremely high pressure, the atoms inside matter are squeezed tightly together. How tightly? At this point, the electrons outside atomic nuclei are forced out of their original orbits, and are all squeezed into orbits extremely close to the nuclei. Originally, there is an enormous amount of empty space between atomic nuclei. If an atom were a soccer field, the nucleus would be like an ant on the grass. But in matter in an electron degenerate state, the range of motion of electrons is drastically reduced, and there is no longer so much empty space between nuclei, where an ant once needed to cross an entire soccer field to meet another ant. Now, when it looks up, ants are everywhere. Although it is extremely crowded, this electron degenerate object, a black dwarf, is very stable. Because its mass is limited, it cannot continue to compress the electrons inward, and force them into atomic nuclei to form a neutron star. So for a black dwarf, the electron degenerate state will accompany it for its entire existence, until it encounters one particular process, quantum tunneling. In the quantum world, the existence of the uncertainty principle allows microscopic particles to appear anywhere. For two atomic nuclei that are already extremely close together, there is an exceedingly small probability that they will fuse through quantum tunneling. Although the probability of this kind of cold nuclear fusion is incredibly low, given enough time, even the smallest probability becomes inevitable. Moreover, for stars of small to medium mass like the Sun, fusion typically proceeds only as far as carbon and oxygen. So the white dwarfs and black dwarfs they form theoretically still retain some potential for further fusion. After a black dwarf has existed for an unimaginably long time, the carbon and oxygen in its interior will gradually fuse into iron. Although this process occurs extremely slowly, it is precisely this slow change that plants the seeds of collapse in an already frozen black dwarf. For oxygen and silicon, the ratio of protons to neutrons is relatively balanced, roughly half protons and half neutrons in the nucleus. But iron has a much lower proton fraction. It contains several fewer protons than neutrons. During the fusion process that leads to iron, the excess protons are converted into neutrons through electron capture. Each such conversion consumes one electron. That means that for every iron nucleus formed, approximately 2 electrons are consumed. As electrons are continuously eaten away, the decreasing number of electrons weakens. The electron degeneracy pressure. When the electron degeneracy pressure is no longer sufficient to support the interior, the long-frozen black dwarf is reawakened, and begins collapsing toward the center once again. What happens when a black dwarf continues to collapse? There are two possibilities. For relatively massive black dwarfs, as the core density increases, the iron core begins capturing electrons, further weakening electron degeneracy pressure. As the core density continues to rise, the boundaries of atomic nuclei begin to disappear, and protons, neutrons, and electrons gradually merge together. Eventually, neutrons come to dominate overwhelmingly. At that point, the black dwarf becomes a neutron star. the newly formed neutron star's temperature will surge once again, but this process is more like a final flash of brilliance. It will soon cool down again, and become a black neutron star. For low-mass black dwarfs, their interiors are already almost completely iron, with virtually no outer layers remaining. In this case, the gravitational potential energy of collapse cannot be released in any other way, and is instead unleashed directly in an explosion. As a result, the black dwarf ends its life in an event similar to a supernova, though far less luminous. No matter which outcome occurs, the most astonishing aspect of this process is the timescale. Scientists have calculated that massive black dwarfs would explode first, after roughly 10 to the power of 1,100 years. That's right, a 1 followed by 1,100 zeros. Low-mass black dwarfs would take even longer, with explosions occurring around 10 to the power of 32,000 years. At this scale of time, you may no longer have any intuitive sense of what it means. For comparison, Hawking radiation is already incredibly slow, right? An ordinary stellar mass black hole needs only about 10 to the power of 67 years to completely evaporate through Hawking radiation. Even a supermassive black hole at the center of a galaxy would take only around 10 to the power of 100 years to evaporate. In other words, in the distant future, what remains in the empty universe may not be black holes, but black dwarfs. And as black dwarfs eventually explode, everything in existence will cease to be. By then, there will be absolutely no flow of energy, and the universe will enter the era of heat death. Seen this way, Hawking radiation doesn't seem all that slow after all. Hawking radiation is essentially a phenomenon known as the Unruh effect. This effect does not occur only around black holes. In theory, any object with a gravitational field should exhibit it. Neutron stars, white dwarfs, and even all matter in the universe should experience Hawking radiation. It is just far weaker for these objects. If white dwarfs also emit Hawking radiation, can black dwarfs really survive for so long? Or does an object like a black dwarf even exist at all? In May 2025, a paper published in the Journal of Cosmology and Astroparticle Physics examined the evaporation of black holes, caused solely by spacetime curvature, even in the absence of an event horizon. Through their calculations, the researchers found that the evaporation time of an object is inversely proportional to the 1.5 power of its density. Based on this, one can estimate that, ignoring other factors, a human body would require 10 to the power of 90 years to evaporate via Hawking radiation. The moon would require 10 to the power of 89 years, and a white dwarf would require 10 to the power of 78 years. From this, we can see that, once Hawking radiation is taken into account, the lifespan of a white dwarf is actually nowhere near as long as previously imagined. It is roughly comparable to that of a stellar mass black hole, and would never even last long enough to become a black dwarf. If black dwarfs will never form in the universe, then that also means the end of the universe may arrive much earlier than we ever expected.